Okay, so the first one, what's going on there? Which, A, B, C, or D? What is that? C. It looks like a line. It has a positive slope, so that's a linear increase. And then you match it to which one of those pictures is a linear increase? The first one. Okay, so I'll press pause and you finish if you aren't already. So number 2, it's exponential something. Is that one growth or decay? So what's the difference between the key thing is not the number out front, but the number that has the power on it, if that helps. So if I multiply by 1.2 a bunch of times, it's going to grow. It's going to grow. So that's growth. And then the picture that matches that growth would be number 3. Thank you, sir. Number 3, we're back to a line, so that would be linear decrease, and that would be 4. And then lastly, number 4, the multiplier is 0.5, so we're going to be multiplying by 0.5 a bunch of times, so that will be decaying. That will be B, which is 2. Maybe we should label those on there. So growth and decay. Okay, so there's the names and the graphs. Let's do a couple problems with them. Although I need to write one equation down. There's not much room for it is the problem. Let's put it right here. Y equals A times B to the X. A is the starting amount. How much money or fish or population or cobalt or carbon or whatever, that's the starting amount. B, you could label a couple different things. The growth factor, or you could just call it the multiplier. What are we multiplying by each time? And so the B will determine whether we're growing or decaying. So what types of values would make us grow? What types of values of B, especially if you look at those previous 2 examples? 2 would make us grow. 3, 4, 5. So what about, so like where's the cutoff between growing and decaying? 1 is the cutoff. Multiplying by more than 1 will get bigger. Multiplied by less than 1 will get smaller. That's a good question. What happens if you multiply by 1? Nothing. You just stays the same. So there wouldn't really be a growth factor at that point. So if B is greater than 1, we have growth. If B is between 0 and 1, we have decay. Now, we don't really have to worry about those extremes, but yes, if B is 1, then you're just multiplying by 1 every time, and so whatever your value is just staying the same. What about if B is 0, the other end?
Then it's just 1. It's just not like it is.
What would happen if we multiply by 0?
0.
We get 0. So we'll never do that because that wouldn't really be exponential decay. That would just be going from 5 to 0 and then you're done. So we won't really hit the endpoints, but that's why we don't include them. So B between 0 and 1, multiplying by like a fraction or decimal, that decreases our amount, that's decay. Anything bigger than 1 will grow. And then X is always what an exponent does. That's how many times we multiply. So just say number of times. Sometimes it's years, sometimes it's months, quarters. I guess it's usually years, but it doesn't have to be years. Okay, so let's try number 5. Sarah bought 5 fish. Every month, that sounds important. Every month, the number of fish she has doubles. How many fish will Sarah have after 4 months if she keeps all of them and the fish stay healthy? Right, so we're assuming they don't die here. So, yeah, some of you got the answer already, but let's fit it into the y equals a times bx model here. So a is what we start with. So what was the starting amount? 5. What's our growth factor or our multiplier? 2, because we're doubling. And how many times are we doubling? 4. So 5 times 2 to the 4th. I think we can get a calculator on this because some of these answers will be bad. But 2 to the 4th is 16. 16 times 5 is 80. So 80 fish. Number 6. A population of 450 animals, sounds like a starting point, decreases at an annual rate of 16% per year. Find the number of animals left after 5 years. Okay, a times b to the x, starting with 450. All right, here's where things get tricky. What's the multiplier going to be?
16.
Yeah, that's what. It's not 16 because it's going to go down by 16. So just think about if we started with 100 and we lost 16% of them, how many would we have the next year? We would not have 16 of them. It's going down by 16%. You'd have like 84 of them. So 0.84 is the multiplier. 1 minus 0.16 is 0.84. Right, so I mean, if you multiply by 0.16, then you would have to subtract that from 450 and do that 5 times. But it's just easier to multiply by 0.84 5 times. That one would need a calculator, unless you know what 0.84 to the 5th is. So 188. And I guess we should round to the nearest animal, because parts of animals don't seem quite right. Okay, but the big thing on that one is, if you're decreasing at 16% per year, your B is 0.84. You got to do 1 minus the decrease rate. Why don't you try number 7? You know what depreciates means?
Go down.
Yeah. So you try number 7. Grab a calculator, because I think you'll need it. Jack, what did you say your answer was?
9,843.72.
It sure is. $9,843.72. But yeah, if you lose 15% per year, you're losing a lot. All right, let's skip down to number 9. Radioactive carbon-14, so this will sound like chemistry here, has a half-life. Half sounds like a multiplier situation. How much of a 100-gram sample will remain after 11,460 years? Well, what's our starting amount? 100. What's our multiplier?
0.5.
Yeah, 0.5 or 1/2, whatever you want to put in there, because that's the same thing. Now the trick on this one is, how many times do we get cut in half? Where'd you get twice from? You're right.
The half-life is 5, 7, 30 after. Yeah.
So you got to do a little math on the side here, or you can just put it into the equation. If it cuts in half every 11,460 years, then if we divide that by, well, that's 2, so we don't have to use a calculator for that. We'll cut in half twice. Now, it doesn't always turn out to be a nice integer, but whatever that division gives you, that's how many times, that's what you use for the exponent. I don't need a calculator for this one, because 100 times a half would be 25. I don't know the answer to that yet. Yeah, it doesn't fold over real well because there's 100 pages in that book. There's not 100 pages. I didn't even count. I don't want to know. I don't want to know. All right, number 11 at the top of the next page. On the day you were born, your uncle gave your parents a piece of sports memorabilia valued at $75. If past trends continue, it should appreciate in value 12% per year. If you sell it on your 18th birthday, what can you expect the sale price to be? A times B to the X. So what's our starting point? How much is it worth on day one here? 75. What's our multiplier going to be? Good, 1.12. Right? If you just made it 0.12, then you'd be decreasing value every year. You want it to increase by 12%. So 1 plus 0.12. And then 18 years later, whatever we get. 75, 1.12 to the 18th, 576.75. So then the question is, do you really want to sell that, or do you want to keep it?
It should go up.
Guess it, yeah, probably go up more. Maybe it's got some sentimental value, whatever. Let's skip down to number 16. Number 16. You deposit $1,600 in a bank account. That sounds like a starting point. Find the balance after 3 years in each situation. Okay, so this is the old compounded stuff. I don't know if we need a separate formula for this. 1 plus R over N to the NT. I don't know that you need to memorize that because it fits with Y equals A times B to the X. That's really the same formula. Obviously they look very different, but it's kind of the same thing. So most of the time teachers present this like it's some separate formula, but you can just keep using this if you have your brain turned on. Part A. The account pays 2.5% interest compounded monthly. Okay, so we know we're starting with 1,600. What's B going to be? What's our multiplier going to be? Oh, this is where things get a little bit tricky. Well, that 2.5% is always an annual interest rate. So if we want it per month, we have to divide by 12. That's the R over N part. So 1 plus 0.025 over 12. This is all going to head to the calculator soon enough. So each month, right, you don't get 2.5% per month. It's an annual 2.5%, so you get a 1/12 of that each month. But if we compound monthly for 3 years, how many times will we hit the button to recalculate? 36. 3 times 12. So again, calculator problem here. 1,600. Again, just put it all in the calculator all at once. Don't try to do the thing where you find an answer and find an answer and find an answer. Just shove it all in there. It's not a lot, but 2.5% for 3 years, that's not a lot. So yeah, that makes sense. Thank you. All right, what does quarterly mean? Yeah, careful. Quarter is, there's 4 quarters in a dollar. There's 4 quarters in a football game. There's 4 quarters in a basketball game. Go Rockets. And there's 4 quarters in a year. So 0.0175 divided by, how many times per year are we compounding? 4. And if we compound quarterly for 3 years, that means we'll compound 12 times. So this is almost certainly going to be less than the previous one, right? Because we're compounding less often at a lower interest rate. So this one will almost certainly be less than 1724. Sorry, that's not 4.3. That's 4 times 3. So you were right to be confused about 4.3. That's a good question. Sure enough, less than the other method, which completely makes sense, because lower interest rate, less compounding, of course that's going to be less money. Oh, what do we think about C, though? 4%, but compounded only once a year. Do you think that's going to be more than or less than that 1724 from the first option? I mean, we don't know yet. You haven't done many of these. It turns out that the interest rate is usually far more important than how often it's compounded. So like the number of times, it helps, but because you divide by it, it doesn't help as much as just having a bigger interest rate. So I think it's going to be more, but let's find out. 1 plus 0.04. Well, I guess if we want to fit our pattern here, what should we divide by? 1, because we're compounding once a year for 3 years. So how many times are we hitting the compound button? 3. 1600 times 1.04 to the third. 1799.78. So yeah, you'd rather be compounded more often than not, but the interest rate is more important than how often it's compounded. So let's see, how many more of these should we do? All of them? Let's do it. No, not let's. Why don't you try number 18? A monthly problem, 14 grand, 6%, 10 years. That should be a decent amount of money. 25,471.55. Uh-oh. Did I do something wrong? Anybody else get that? Okay. I mean, most likely you just hit a button wrong in the calculator, Jack, would be my guess.
Yeah, because mine's off by 1 decimal place.
That's weird that it would be off by 1 decimal place, because I feel like...
2,547.
Oh, then you probably multiplied by 1,400 rather than 14,000 to start with.
I did.
There you go. Yeah, most of the mistakes are just going to be punching things in wrong on the calculator. Okay, so the assignment is the rest of them. Not really tricky, I don't think. I like that last one. That one should be close. 5,000 for 2 years, 10%, but only once a year. 9 7/8, 12 times a year, or 9 3/4, 365 days a year. That one's too close to call. I don't know who will be most in that one.